Okay, now that we've kind of talked about what linear and nonlinear are, we're going to look at, representations of this to see what they look like in terms of equations, graphs, tables, that sort of thing. Okay, so this video may run a smidge long, but I want to kind of keep it all in one thing. All right, so really quickly, we're talking about linear, right? That means it makes a single straight line, right? A straight line, and it makes one, right? So it's not a series of them, it's just one straight line, right? And then when we talk about nonlinear, basically, something that's curved or pieced together, right? So it's not, it's not a single straight line, basically, pretty much everything else, all right? So now, when we're classifying a function as linear or nonlinear, all right, what we want to do is we want to be able to say, okay, well, is this going to be linear or nonlinear? So the question is, can you write it in this form, in the form of y equals mx plus b? And you guys should hopefully remember this. This is our slope-intercept form, right? And that's the parent form of basically everything that can be graphed as a straight linear equation. Okay, so so let's take a crack with this first one here. So if we have 2x plus 3y equals 8, and hopefully you guys kind of remember, like, oh yeah, if we're going to write it in y equals mx plus b, right, we got to rearrange some things. So first thing we got to do is we got to get this 2x over to the other side of the equation, right? And the two ways you can think about that is either just subtract it from both sides, right? Or you can think about it as when you move this across the equal sign, it changes signs, right? So when you change sides, you change your sign, okay? So either way, it puts it on the other side of the equation, and you get negative 2x plus 8. Now remember, you can't combine these two because they are not like terms. All right, this is Algebra 2. We should have a grip on that by now. Okay, and then the last thing is, if we're going to be able to put it in this slope-intercept form of what we've got right here. Sorry, this is already a mess, but this thing right here, right? If we're going to put it in this form without this being in it, right, y has to be by itself. There's no number in front of y. Okay, so that means I got to divide this by 3, and I got to divide everything over here by 3. So when I do that, I get y, and then we can split this up. So negative 2x divided by 3 just gives me negative 2/3 x, and then plus, and then we got to take this right here, 8 divided by 3. Is this in y equals mx plus b form? Yeah, sure is, right? Here's my slope. That means this thing goes down 2 over 3, my slope, and it crosses the y-axis at 8/3, which is almost 3. Okay, now this one right here, okay, you've got, let's rewrite this p of x just as y, right, over 2x. Now if I'm going to write it in y equals mx plus b form, right, I got to be able to have the y by itself. And, remember, b can be 0, right? But x in this always has an exponent of 1. Well, the thing is, x here does not have an exponent of 1. If I were going to write this with an exponent, now I don't know if you guys remember this, but when something's in the denominator, you write it like this. It's 2x to the negative 1, right? And that is not 1, right? 1 and negative 1 are not the same. They're very different, right? And this actually is going to give you something that's going to give you a really, really crazy zany curve, right? It's just going to be nuts, right? It's going to give you something, that's going to more or less look like this, right? And we call those exponential, functions, but that's just kind of a nuts function. Definitely not linear, right? So this would be nonlinear, all right? Nonlinear. It cannot be written in this form right here. This one, I should have written this down, is linear, okay? So we got linear, nonlinear, right? Now let's look at tables. All right, so for tables, All right, just what you look at is you say, okay, is this thing making a straight line? And letter C is a little deceptive here. So what I want to look at is I want to look at the points. So I also know that it should be constant rate of change, right? So it's going from 100 to about, I don't know, 120 or so. And then it goes from 120 to about, you know, it went up 20, and then it goes up. If it went up another 20, it would be at like 140. Well, that looks a little higher. And then it goes up clearly more than the 25 that should be the distance between these, right? If I look at over there, right, it's going up more, and then it's going up even more between the next two. So, you know, if you're going up like 20 and then, you know, a little more than 20, we'll say 22, and then this one's going up, you know, I don't know, maybe 26. This one's going up, you know, close to 30. It's not the same, right? And if we, you know, and there is a slight bend to this. So that is intentional, right? And that would make this a non-linear graph, all right? So the function is non-linear. Okay, and if you look at what they're talking about the population of an area, right? And they're saying, you know, the time in years, right? So that is, that would be called, you know, more exponential growth. All right, now we look at this one right here, right? It's 100 to 125, goes up 25 over 1 year. This one, 125 to 150, goes up 25. 150 to 175 goes up 25. You see what's going on here? We have a single straight line, and we can verify that with the points. So if it's not readily obvious through looking at it, you can just check the points. And so this one is linear. It makes a straight line, and it has a constant rate of change, right? It has the same slope throughout the whole thing, right? So that's what you're looking for graphs for these. And then for tables, this is what you're looking at, okay? And this can get a little confusing, but we're going to you always call this X and Y, right? And this one, it's already written as X and Y. And just look at how much does it change. All right, it's going up 10, right? It goes up 10. Here it goes up 10. And here it goes up 10. So you might be tempted from seeing that to go, oh, it's got a constant rate of change, but we don't know that yet. We have to verify that this also is the same here, so we have the same ratio, because remember, your slope, your rate of change is always y over x, right? That's your slope, and then it's also the same as your rate of change, okay? So all different words for the exact same concept, right? This one goes up 1.5. From 1.5 to 3, it also goes up 1.5, and it continues to do this throughout the duration of these values. And so you always have this value right here, right? 1.5 over 10, which is the same as 0.15, okay? So that's my rate of change, right? Or you could also call it 3/20ths, whatever you want to call it, right? But that's my rate of change. It is the same thing, right? It's 1.5 over 10 right here. Here it's 1.5 over 10 and the same. So it is the same throughout. So because it is the same, right, that means that it is linear, because it will make a straight line if we were to graph this, right? And if you don't believe me, get some graph paper and throw it on there and you'll see. All right, now this one right here, right? We're going up 10, all right? That's promising, okay? And then this is going up 1, right? So you got 1, it's going up 1 over a rise of 10, right? So we got 1/10. All right, that looks good. This one, it also goes up 10. All right, I'm going to use plus signs here. And this also goes up 1. So again, we have 1/10, right? Excellent. This goes up 10. Well, this is looking promising here, right? This goes up 1. Sorry, it's not T1, it's plus. All right, so we got 1/10 for this one. This last one, let's see here, it goes up 10, that's good, and then it goes down 1. So now we've got this. So even though it was doing this right here, now this happened. So this right here is the deal breaker, right? This is not the same as these, right? It is very different from from our what we had a constant rate of change going until we hit that. And at that point, the graph stops going up and it starts going down. So this could be a graph of an absolute value equation or something else, or a piecewise function, but whatever it is definitely not linear. And I can tell all of that just from looking at this one right here and seeing that this is different from the other three. All right, so this is the deal breaker. This one is the one that we have to be able to see that, oh, one of these things is not like the others, right? And that is the case with this. Okay, so not linear. So that's what we're looking for in all these cases, right? Is just you're looking for inconsistencies basically between the rate of change, whether it's in the graph, the equation, or whatever it is. But it's, you know, there's definitely things we're looking for that if they aren't there, we know then that it's not linear, and then we call it non-linear, right? That's the other, I wrote not, but it's non-linear, right? So something other than a single straight line. All right, thanks for watching. Hope this is helping, and we'll see you soon.